Uh, with the rapid development of new internet technologies, the world's communication demand is growing rapidly. It brings great challenge to the optical transmission system. We can see that space deviation multiplexing, wavelength deviation multiplexing, and modulation technology are the main method to improve the transmission capacity. According to the current development rate of computing technology, it's estimated that the demand of optical transmission system capacity will reach 100 Pbit per second by 2038. The conventional WDM optical transmission system based on C and L band use a wavelength window less than 80 nanometers. It has shown bottleneck problem to with bandwidth requirements. In the future, OE and S band can be applied to increase the capacity of WDM transmission systems. At the new extender window, the S band has great potential to increase the capacity of conventional C and L band-based WDM transmission network. The main resistance to deploy S band is fiber inherent loss and amplifier performance. Recently, with the deployment of new Raman amplifier and TDFA, the throughput of S band has been greatly increased and already comparable with C and L bands in the single band transmission, which is promising for data center and virtual network. However, compared with the low-cost conventional EDFA, the deployment of TDFA as a receiver side of S band may bring higher cost than C and L band. The low-cost SOA will be more suitable to in short distance transmission for S band. To verify the performance of SOA, we first compare the SOA and the GDFA with 48 Gbaud DP16COM format in S band, 1495 nanometers back-to-back transmission. The setup and the result is shown in the figure. At 0.02 FDC ratio compared with the GDFA, the performance penalty of SOA is less than 0.5 dB. In the WDM transmission system with a large number of channels, the deployment of SOA in receiver has more benefit in economical efficiency than TDFA. So with the SOA assistance in S-band receiver, we built up a SC and L-band transmission system over 50 kilometers, G.654.E SSMF. The transmission signal includes test channel band and low measurement band. The test channel band generates modulated signal and low measurement band produce VSE field channel to simulate a fully loaded WDM system. The carriers of test channel and label channel are generated by label terminators. The modulated format is DP6COM in S-band and DP64COM in CL band. The low measurement band channels are generated from ASC source and combined in WSS to generate dummy odd and even channels. The channel grid is 50 GHz in S-band and 25 GHz in CL band. At the common port of WSS, the test channel band and the low measurement band are combined together. Before transmission, the CL band output signals are amplified by EDFA and then combined together by CL band WDM coupler. The output power of the CL band EDFA and the TDFA are 27 dBm and 20 dBm respectively, due to the lack of SCL band WDM coupler, and in order to balance the output power of the three bands, we use a 20-80 ratio power coupler. 80% power of S band signal is combined with 20% CL band signal. And as the receiver side, each band signal is amplified to compensate the fiber loss. Then, turnable optical bandpass filter is used to select the test channel with an amplifier follow. After the signal detection of coherent receiver, DSO is used to sample the detected electrical signal. After offline DSP in computer, the signal is finally recovered and the BER is calculated. This is the fiber input and output spectrum of the whole band transmission. The wavelength range and the channel numbers of SCL band is shown in this table. The total fiber launch power of the wideband signal is around 22.9 dBm. The launch power of SCL band are 18.1 dBm, 18.7 dBm, and 18 dBm respectively. At the output terminal of the fiber, the received power of SCL band are 6.4 dBm, 8 dBm, and 7.4 dBm respectively. The transmission performance of all channels is measured and the result is shown in the figure. The signal is modulated by 48 G-baud DP60 in S-band and 24 G-baud DP64 in CL band. Due to the amplifier performance, inherent loss of optical fiber and the performance of optoelectronics device at the transceiver, the performance of S-band is lower than that of CL band. From the measured result in 50 kilometers, G.654.E fiber transmission, BER values for all channels are below the FEC's ratio of 0.02, assuming the soft decision FEC. This translates to a raw transmission capacity of 155.52 TBs per second for 50.1% coding per head. And finally, the conclusion, we demonstrate 155 TBs per second wideband transmission with 120 S-band channels spacing at 50 GHz and 380 CL band channels spacing at 25 GHz over 50 kilometers, G.654.E fiber. The signal is modulated by 48 G-baud DP16 in S-band and 24 G-baud DP64 in CL band. Based on SOA in S-band receiver, the capacity of S-band is similar to common CL band. This result shows the potential of low-cost S-band deployment to extending transmission systems. That's all. Thank you for your attention.